testing on this microphone. Everything looks good. Go back to Keynote, get some. All right. So, hello. I'll have this slide up as my first slide. Oh, it's just a way to break the ice while I'm, getting set up. Maybe my microphone won't be on. Okay, so who knows who this person is? This is the first sort of patriarch of the Medici family. Medici family was a family in Florence who they were bankers, and they became super powerful. Probably the wealthiest family in Europe, non-king, non-royal family. How did they do that? That is one of the mysteries of this talk. What did they do to get so powerful as just regular bankers? Let me give you a little intro about how powerful they actually were. They actually had 2 regent queens of France that came from their family that married into the French royal family that sired multiple kings of France. 2 queens of France that weren't regent, meaning regent means that they actually ruled while their sons were too small to rule. Queen of England also. They had many dukes and archdukes in Italy, and also 2 popes came from the Medici family. So why am I talking about the Medicis here? This was back in like the 14th century. They were super important as bankers, but they were important not just because they were, quote, good at banking, good with money, but they developed a particular abstraction. That abstraction is the double entry bookkeeping system. Double entry bookkeeping is the system that we still use today. They didn't invent it, but they did make it mainstream to use. They developed a lot of the refinements on the double entry bookkeeping system. But it is one of the keys to their success at becoming, the most powerful family in the world. And this is the kind of thing that a powerful abstraction can do for a business, say. It can be this sort of bedrock of power base, really capturing the essence of banking into a simple system that you can implement and just refine and make it super solid, take over the world. Okay? So what are some of those characteristics of this system that make it different from other systems? One is that it actually has this equational reasoning that you can do with it. There's laws that are followed in the system. So one of them is double entry means every entry in your accounting has to have a debit and a credit. And so if you add up all the debits, they will equal the sum of all the credits. And people talk about that like, oh, it's great for checking if you've done it right, because if they don't add up, that means that you've made a mistake somewhere, you missed an entry, or you only entered 1/2 of a transaction. And that's important, but I think it doesn't get at why they were able to take over Europe. Here's another equation that you get in double entry bookkeeping. You have assets equals liabilities plus capital. These are all different accounts. So double entry bookkeeping as an abstraction has certain concepts. One of those concepts is an account. And if you have a liabilities account and a capital account, you add them up, it should be the same as your assets account. So we can sort of talk about this a little bit more like as programmers. I'm not going to give an accounting lesson, but one thing that is cool about double entry bookkeeping system is you have this reasoning. So if you have on this side of the equation, you can add a transaction to your book, right? Because the book is like the register of all the accounts and what's happening at the bank. If you add a transaction to the book and then you add another transaction to that book because it returns a new book, that's the same as adding the second transaction first and then adding the first one. Okay, so basically what this is saying is the order of transactions doesn't matter. Okay, and that's something that we can express mathematically that, say, another accounting system you couldn't do. All right, so if you were in JavaScript, this is the kind of thing you would see if you wanted to like represent a transaction. You can see, of course, it has an ID because you want to be able to talk about it later, give it a name. But it really has three components that are important: the amount, the debit account, and the credit account. Very simple abstraction. It is basically, as good abstractions do, eliminated all the unnecessary stuff. Just three things remaining. And then, of course, an account, you have an account is just a list of debits and a list of credits. It's easy. So what does this abstraction represent in the real world? I get kind of annoyed when I hear people talk about abstractions when they don't even know what the concretion is of that abstraction. What did you start with to abstract away? You can't just say, oh, I made a class or I made a function. Well, what is it actually abstracting? So let's do that exercise here. What is this double entry bookkeeping abstracting? And that's a real question for the audience. Just shout it out because I can't see hands. And of course I would wait here, but I can't wait forever. So really it's about gold, right? We had a number, that's the amount, but it's money, right? It's gold. So that's important to remember. But more than that, an account is the amount of gold in a vault or a safe, right? So that account is the safe that the gold is in. And a transaction represents motion from one account to another. Okay? So this is the key insight of this abstraction. The key insight is that you don't just keep track of how much gold each person has, how much gold is in each account, because I mean the gold kind of takes care of itself. Like if you keep that safe closed and then you open it later, you can just count the gold. Like you don't really need to keep track of that. Now, of course, you might keep track of it at the front desk so that people can ask quickly without you having to count and measure and weigh. But you don't have to. But what this thing actually is keeping track of is the motion of gold. That gets lost. If I move a bar of gold from this vault to this vault, I've forgotten where it came from because the gold is all the same. You can melt it down and it's a fluid quantity. So the key insight and the reason it's so powerful is not because of that error correction or error detection mechanism of the sums being equal, but because it's keeping track of the history. Okay, so this is what I'm contending, that a good abstraction has this power over other abstractions, that it's more useful in that sense. So this transaction history is what makes it so powerful. That's the thing that gets lost in the real world. But by writing it down, you now have gained something over that. It becomes an information system that is adding to the value of the physical system that it's representing, that it's abstracting over. All right, so we've gone from abstract, the double entry bookkeeping system with accounts and transactions and ledgers, and we've reverse engineered like what would a bank look like without it, right? This is the physical aspect of it, the physical representation of it. But really as programmers, what we want to be able to do is go from that physical to the abstract, right? We're given a problem. Usually it can be a physical problem, like I need to keep track of X, Y, and Z. And now we want to develop abstractions that let us do that. So, okay, here's a tweet. If you have your phones out or your computers out, I see a lot of you. Here's something that you can tweet. I've measured it, it's tweetable. As devs, we are professional abstraction builders. We build double entry bookkeeping every day. Okay? We have this power of building an abstraction as powerful as double entry bookkeeping every day. And we're kind of squandering that power. Now, what I would like to present, my name is Eric Normand, yes, if that's not clear. What I would like to present is a process for doing that, for taking a problem and turning it into an abstraction that is powerful, free from leaks, from abstraction leaks, and potentially gives you a direction to go in to implement that abstraction. So let's get started on this process. I've been programming for a number of years, and especially when I was first starting out, I would get this kind of advice. Don't just start writing the code, think about it first. And it's true, you can't even argue with it. It's like, duh, yes. You should always think before you do something important, whatever. But the thing that it doesn't tell you is how to think, what to think. Sure, I can think, but like, what should I be thinking? It's always been my question. So this is the process that this quote kind of gives me an idea of, like, as precise as it is. So you're working, or you need some work, so you pull a Jira ticket. Instead of just starting to implement it, you think about it, then you implement it. Okay, I mean, that literally just sounds like procrastination, right? And so that's what this process is. It's going through number 2 and sometimes number 3 to make it better. All right, so some objectives for the talk, for this process, really, not for the talk. The objectives for the talk, we can talk about that later. But the process needs to generate consistently robust abstractions. So the process needs to be followable by anybody, and when they're done, they either have an abstraction that is robust, or they know they don't, and they can iterate through again and clean it up and make it better. Also, I would like the process to be collaborative. We program in groups, on teams, and so we need to be able to do this together, not just one person, one genius like sitting in a room somewhere inventing double entry bookkeeping on their own. It needs to be done together. All right, so let's get to the steps of this process. We're going to go through an example, like right after we go through these steps, so you'll see how each of these things work. Okay, so the first step is you need to start with a physical metaphor. We'll go deeper into that. But this is the thing that you're going to abstract. Never abstract without knowing what you're abstracting. It doesn't make sense. It doesn't, you're abstracting something, I don't know. All right, then once you have that abstraction, that concretion, that physical metaphor, You can mine it. Because when we have a physical metaphor, it's something that we can reason about intuitively. So we can mine that, we can sense it, we can talk about it in a group and really understand how that, what's important about it, so what needs to be in the abstraction and what can be left behind, and what kinds of rules and laws we can develop based on that intuition. And finally, implement it. Sometimes, especially in a functional language, you can go from the specification and it looks exactly like the implementation. Like there's no, like you can't even see a line where it's like, okay, now I've implemented it. Like no, it's just so clear how to implement it from a specification. And so sometimes that will happen. Doesn't mean it's like an efficient or the best implementation, but it is a correct implementation. And sometimes that doesn't work quite so well. Though you will know there are ways of turning your specification into something that is more implementable. And we'll talk about that. Okay, so I've given this talk once as a practice, and this is a stumbling block for a lot of people. I say this, to me it seems kind of obvious because I've lived with the idea for a while. But for other people, this is where I get a ton of objections. So every idea has a physical component, has a physical metaphor. Okay, that's the idea, that you can take any process, any thought process, anything, and turn it into a physical metaphor. This is something that just seems so obvious to me, but the way we think about the world is way more physical than we often think we do, than we're aware of. If you look at all of the metaphors of speech, all the words that we use to talk about ideas and thinking and stuff, like I gave him an idea, right? You gave him an idea. Really what you're saying is, oh, I talked and the person heard me, and then that gave them, then they had the idea that I had, right? But giving them an idea is like physically handing them a thing called an idea. Like we're using this language of motion and personal property and stuff that just doesn't correspond all the time, but that's what we're using. That's how we're thinking about stuff in our heads all the time. Further, if you read a book on the thought processes of mathematicians, this kind of bugs me. Like mathematicians will do all sorts of cool equations, and you think, oh, they must be thinking in all these symbols, very abstract stuff. But when you ask them to describe how they came up with that, it's all either visual or the better mathematicians, the one that are like more innovative in the field. Often it's very physical. How they think about it. They think about it in relationships, spatial relationships and stuff. And it's very imprecise. And so they have to express it in the precise language of mathematics in order to be able to communicate these feelings and ideas that they have. As an example, you might say, oh, the theory of relativity, it's so abstract, how can you understand it? Well, Einstein was doing thought experiments of what would it be like if I were riding on a photon moving at the speed of light. Right? That's a very physical metaphor kind of thing. That was he was mining that intuition of what it would look like, And then later, he struggled with the math. He needed help to develop that intuition into mathematics. So that's the kind of thing I'm talking about. Like, we need to bring it down back into a physical thing before we start abstracting. So we talked about how the accounting is actually, the physical representation is moving money from one vault to another, moving gold, let's say. It's not about counting money, right? You're not, that's part of it, but the main thing, the main difference between double entry and some other accounting system is that you're tracking motion. You're representing motion in an information system. So let's talk, just a tiny bit about this other problem, just as a simple example. So you are tasked with developing an information system to allow students to register for classes. So obviously a student is going to have more than one class on their schedule, and the classes are going to have a bunch of students in them. And you want to keep track of it. You want to limit the number of students in each class and make sure that they don't have two classes at the same time, all that stuff. So the kind of way I was taught to model this problem, and this is, at a school, at university, the way I was taught was, well, you describe the problem in a sentence, or a paragraph, and you underline all the nouns, and you make classes out of them, and then you underline all the verbs, and you make those methods on the classes. So you would have a student class and let's call it a course class, and then you would have register as a method on the student, and probably register on the class. And then if I did student.register, and I would pass it in the class, and it would, call register on the class with itself, and they would kind of keep in sync that way. And the student would then have like a list of classes that he was in, and then the class would have a list of students that have registered for it, and then you could have some logic like, oh, there's too many students, so you throw an exception or something. Okay, that process itself is kind of baloney. I have a whole talk about that, which I will put a link in my slides. I should do that. I have a whole talk about why that whole process just doesn't make sense. But it is a process, and I can follow it, and I can get a program that kind of works, and then just work a lot to debug it. But the abstraction it gives is totally leaky. Totally leaky. There's all sorts of problems with it that are well known. But the thing is because I didn't sit down and think about what is actually going on there. What I did was I started with a description of the problem. Students need to be able to register for classes. And I just, I worked from an already abstract version of the problem, right? That abstract version of the problem was this, high-level description of what's going on. What I should have done is kind of zenned out for a minute and been like, wait a second, what is actually going on at the school? So let's sit in our time machine, our mental time machine, and go back to a school before they had computers. What did they do to register for a class? Well, I can't go back really, but I can imagine, right? I can imagine that they would have an office with someone in the office. And as a student, I would go into that room and I would say, hey, I want to register for this class. And they would open a book, big book because there's a lot of students, and they would turn to a certain page, and then they would write down my student ID and the class that I wanted to be in. They might check, yes, there is still room in that class. You have all the prerequisites, all that stuff. But they're basically writing down an intent of this student with this ID to register for this class. Okay, so I now have a metaphor. I'm not actually implementing students registering for classes like I was in this, other process. I have this metaphor of I'm representing this book and all the rules that this, let's call that person a secretary, all the rules that the secretary was following to get my information into the book. Okay? And so then we can go through and say, well, there's a many-to-many relationship that this book is representing, and now we can start to mine it for abstractions. All right, so that's the first step. Second step, develop the meaning of the abstraction. So this is, if you're in a team, this is where you're just discussing what the thing is, what that physical thing is. So now you start talking about that book. Okay, so you have the book and you say, well, it's append only, right? Like someone can register for the class, but we're never going to go and scratch out somebody from a course. We might put another line that says, oh, this person chose not to take this course now. And so, you can start to talk about it. That might not be the choice that you make as a group, but that is a possible discussion point that you could have. And now that you have a physical metaphor of a book, you can actually talk about it and have a conversation where you're actually communicating. You have a common understanding, because everyone has an understanding of a book and a person writing in a book. Like, it's something that we all know. This brings up another point, which is that sometimes we don't have the domain knowledge that we need. For instance, I'm not an accountant, so I wouldn't trust myself to write an actual accounting system. But I can bring the accountant into this discussion, and we can develop this discussion, this abstraction together. Now, one of the things about developing the abstraction is you want to develop its meaning, right? So you're figuring out what do the parts mean. So what does it mean when I write down a line in that book? What the bits of information mean? So the first column is the student ID, the second column is the course ID, etc. And this distinction between implementation and meaning is something that we kind of already have an idea about. So this is the same distinction that we have about the distinction between interface and implementation. Interface is another way of saying API. So this is actually where we're developing the meaning, the API. What does it look like to use this abstraction? Not how is it implemented, but what does it mean? What does it mean? We have to, before we go to step 3, which is implement, we really need to have a meaning, okay? And we need to develop that meaning into something very precise. And so we'd like to use something like mathematics. So this talk, I actually should say this before, but Conal Elliott has a process that he calls denotational design. And this talk was actually in the abstract of the talk. I've actually mentioned that I was going to be teaching denotational design adapted to Clojure. And while that is true in a sense, I believe that Conal Elliott has a very precise idea of what denotational design means, and I don't want to call what I'm doing denotational design. So what I'm teaching now, this process, because I think that's his thing and he has a meaning for it, and this is largely inspired by it, but is also my interpretation. So I just want to be clear. He has 3 principles that I think are excellent. You want your abstraction to be adequate, meaning it does the use cases that you need. Simple, and by this I know in this audience we have a definition of simple. It's not the same. Simple means doesn't have anything it doesn't need. So if you can express something with fewer parts, you should choose the fewer parts, and also that it's kind of clarifying, like it lends some new ideas to the abstraction. So you might have a physical process which is actually a mess, but by abstracting it, you can actually say, oh, it's actually not. If you look at it this certain way, you eliminate the messy parts. Ooh, you've actually got something that I can actually understand. So that's what he means by simple. And then precise. To him, it's not so important as like a fundamental principle. The first 2 are more important, but precision keeps you honest. It's really easy to be simple because you're just kind of hand waving around things. Precision is what makes the other 2. It keeps check on the other 2. So adequacy, can we express every use case? So I'm trying to talk about them more in like software engineering terms, because that's what we'd like to be doing, and that's what we mostly do all day. So I'm going to go out on a limb and say simplicity in this sense are the parts separate but related? And is there a small amount of boilerplate? The boilerplate for things is usually an indication that you haven't quite captured the essence of the thing in your abstraction. And precision for a software engineer means I can write a test and say yes or no, this does what it's supposed to. Okay, so at this point, this is where I'm going to do I have slides that actually build an abstraction about, that uses this process, like step 1, steps 2, step 3. And it's going to be graphical. It's going to be using Quill. So I first want to show that Quill does not do what I want it to do, and then show how we can build on top of Quill a new abstraction that does what we want to do. And unfortunately, I don't have those slides, so I don't really want to talk through it yet. Okay, so after we do that, boom, this is Isaac Newton, kind of a handsome guy, lived in the time of wigs, It was the fashion at the time because kings liked to wear wigs because they were getting older, losing their hair. He said this thing. It's not like an original quote. This wasn't him originally, but he said this. Partly he was trying to make fun of one of his rivals who was short, but it's often taken as like an expression of humility, and I don't see it that way. I see it more as a method, and he was not trying to be humble. He was trying to say, this is what I did, you can do it too. All you have to do is, study really smart people from the past, and then just add a little bit. And if you study enough, you're already pretty high, and then you add just a little bit, and you're like higher than everybody else. And the thing that I think is often, we haven't really figured out yet, but I'm going to contend is the case, is that we actually are standing on so many giants now that we can be an Isaac Newton like every day. Like he had to develop calculus, and we get taught calculus in public school. Like high schoolers can learn calculus. And it was very difficult to develop it, but a lot of people have added to the educational side of calculus so that it's become something that's teachable and learnable in a matter of years, and you can just know it. You can just start from there, whereas Newton had to start from, scratching on paper, right? Just algebra. He also developed what's called Newtonian mechanics, which has 3 laws. Oops. It's an abstraction that's super powerful that everyone has to learn. As if you're going to be a mechanical engineer, you literally can't do without it. Just like an accountant can't become a certified accountant without learning double entry bookkeeping. But the thing is, he had to come up with the formulation for those laws. Now we just get them for free. I mean, with the internet, with people having explained this in different ways and making YouTube videos, like all of this, we have so many giants. I'm going to contend that the giants are exponential. Add to that, we have computers. So we have this tool, we as programmers can, and it's unfortunate that we haven't figured out a way yet to get non-programmers to use computers this way. But we have the ability to create abstractions faster than has ever been done in history. We can build a complete, mechanical universe in the style of Newtonian mechanics in physics, visualize it, see if the laws, what the laws do, and play with gravity and forces and stuff like that. We can build double entry accounting in a few hundred lines of JavaScript. Like, we can literally build abstractions faster and throw them away faster than these giants could have even summed up all of the columns of their account. So that's my plea, is that we need to start mining our physical intuition about systems. Stop joking around with abstraction. Actually build real abstractions that are powerful, that are free from abstraction leaks, that can really add value to our business and to our lives in general. Giants are exponential, and we are standing on them. And then we have another boost by having computers. Okay, done. Thank you very much. Oh, yes, okay, I do want to have another slide about resources for learning more about this process that I've developed. So I'll have to have that too, but just want to make a note of that.